screen. The Chemistry Club Chem Club wanted me to remind you of all the activities going on this week for National Chemistry Week. So there were chemistry fun facts around SCOP today. Tomorrow there'll be a guessing game, and then Wednesday a periodic table of starbursts, so you might want to find that. Thursday's mole day. Friday after seminar is Pie the Prof, which I told you about last week. So I'm up to $21 now, so not just 10 cents. So you can keep making donations. And then Saturday from 9 to noon in the Science Center atrium, there'll be a pancake breakfast. Okay. So now we'll start with the rest of our announcements for lab this week, which are up on the board. We're going to start with this week we'll finish experiment 7. The quiz this week for experiment 7 could be over any part of experiment 7 now that we will have covered both of them. Okay, so all of experiment 7 is fair game for the quiz. Also, I recommend bringing a calculator as always. Your experiment 3 rewrite of your conclusion is due this week, so make sure you've got that with you, ready to turn that in with your notebook this week. Clean glassware well before you leave lab each week. So we have a lot of people needing to exchange out glassware or emergency cleanup of glassware. So in order to prevent that, make sure before you leave each week your glassware is cleaned well and dried, or at least has acetone in it so it will dry, and then make sure you're cleaning your hood up before you leave. Be careful. Around in the hoods there could be little bits of glass if glass broke in the hood, so when you are cleaning your hood, use a sponge. Probably wear gloves so that if there was any stray glass in there, it wouldn't cut you. Okay. Same announcement from last week. If you're going to the Global Health Missions Conference in a couple weeks and you are in a Thursday lab, you need to see me today. Next week we'll be doing experiment 8. You need to. So this experiment is a lot like experiment 3 in that there is a lot to be done. And it is very important that you follow directions exactly as they are written in the lab manual, okay? So make sure that you read it carefully before you even come to lab lecture next week so you know what is going on in the lab. Make sure you're definitely in lab, well prepared for the lab. We're gonna have to put some glassware in the oven next week, so the morning labs and afternoon labs will be opening even earlier so that can happen before lab starts as well. And I'll talk about that glassware here in a minute. Next week also your experiment 6 report is due, and then in 2 weeks your experiment 7 report is due, okay? So, glassware for experiment 8. You need your 3-neck round bottom flask, and a 250 or 500 is fine. That's what should be in your drawer. So either one of them is fine, but you want them clean and dry, ready to go this week so that they are all set to go into the oven next week. So no cleaning of this glassware at the start of lab next week. It all needs to be cleaned this week. So during your hour reflex this week, this would be a good time to get glassware all set, okay? So you want it cleaned, and if it's not dry, last rinse with acetone so it will dry over the week. You also want your 1-inch stir bar, so that should be your bigger stir bar in your round bottom flask. It won't melt in the oven. The Teflon pieces from the separatory funnel will. You want your Liebig condenser. You want to make sure that the jacket is dry as well. So just like we dried it out for experiment 4, it needs to be dry again. We don't want to put any water into the oven because that will defeat what we're trying to do. We're trying to get rid of residual water. If we put something that's definitely wet in the oven, no one's glassware will be dry. You need your separatory funnel, and you can take apart the Teflon pieces, just keep them all together. But you don't want any Teflon pieces in the oven, okay? So make sure you keep your Teflon pieces out of the oven. And then you want your 2 glass stoppers ready to go. So all these guys, make sure are ready before you leave lab this week so that you can stick them immediately into the oven next week when you get to lab, okay? All right, so let's start with experiment 7. We're gonna look at the second reaction of experiment 7, so step 2 reaction. And that's, you should be, if you haven't talked about it, you very soon will be talking about elimination reactions and the types of mechanisms. There's an E1 and an E2. This reaction goes through an E2 elimination, okay? And it also can be called a beta or a 1-2 elimination. Betas. That looks more like a B than an actual beta there. And in this reaction, like we talked about last week, it's the dehydrohalogenation is what we're looking at, okay? So it's this elimination mechanism of dehydrohalogenation. So let's look at it here. What is involved with this reaction? So part of what defines an E2 type of elimination is you don't have an intermediate, okay? And so you're going to learn about E1, the difference between E1 and E2. In E2 elimination, there is no intermediate that it's going to go through. It's just going to, the reaction will occur without having an intermediate species involved, okay? And so we are going to use quinoline. This is our base, and we'll talk about here in a minute why we use quinoline. It's our base for the reaction, but it's also our solvent for the reaction, okay? And so it's called what you call a non-nucleophilic base, and the lone pair of the nitrogen on the quinoline is going to attack one of our terminal protons on our methyl group here. We'll lose that, and then we'll also lose our bromine as well, okay? And so there's our dehydro and halogenation. We're losing the hydrogen and the halogen in this step. And then we'll go on to form styrene, okay? So we're forming this double bond here, taking our bromoethylbenzene, and we're forming a double bond. And so this is our monomer styrene that we'll use in the next step for the polymerization, okay? And so this is all the arrow pushing involved for this step. So we're going to put up here why we are using the quinoline. That's a really important part of this reaction. Like I said, it's also the solvent for the reaction, besides just being the base. It's a non-nucleophilic base. So an example of a nucleophilic base would be like sodium hydroxide. This one does not form a nucleophile. It has a high boiling point, so like pyridine. And we'll use pyridine next semester in a similar situation when we need a non-nucleophilic base. But it has a higher boiling point. So its boiling point is about 237 degrees Celsius, whereas pyridine is about only 115 degrees Celsius. And we need to go up to at least 160 degrees. Okay, and so that's why we've got to use this guy. It has a much higher boiling point than 115. Otherwise, we would never make it up to 160. You can't use for this step, and again, you'll in lecture talk about this a little bit more. You can't use a nucleophilic base. So like I said, like sodium hydroxide. Because you could get substitution instead of elimination. And so we want to make sure we only get elimination product, not substitution product. Now, this reaction, we're going to use heat to drive the reaction. So you're going to set this up with your bromoethylbenzene from last week. Oops. It's going to go in your all-in-one simple distillation apparatus. So what you used in experiment 6 to distill your unknown, you're going to use that for this reaction. So your bromoethylbenzene goes in there along with the quinoline and a stir bar, and you're going to heat it up, and the heat is what drives this reaction. So as you're heating it up, you're going to get the reaction to go, and then you're also going to be collecting the styrene as it forms, okay? So you're not going to just heat the reaction to make the styrene and then do something else to actually collect the styrene. You're going to be heating and collecting at the same time, okay? And so the styrene, you want to collect that between 120 and 160 degrees Celsius, okay? So in your sidearm test tube, just like you used for experiment 6 for the majority of your unknown, that's where you want to be collecting your styrene, okay? You want to only collect over the range of 120 to 160. So you don't really want anything too much before 120, and you don't want anything after 160. You'll stop your reaction at 160, okay? So thoughts on what could come before 120 for this reaction? Any ideas from potentially last week, maybe? The hexane, right? So low boiler could be hexane at about 68, 70 degrees or so. You want to know that volume because you can figure out how much hexane you collect this week and subtract that volume from the volume you have for your product from last week and recalculate your yield of your bromoethylbenzene, okay? So make sure you get the volume of hexane that you collect here, okay? And you want to collect this separate from the styrene. So keep the low boiling guy separate from the styrene. Basically everything up to 120 keep separate from the styrene, okay? So you may want to get your hexane first, and then if you have anything that boils above the hexane, then collect that separately, but also keep it separate from your styrene, okay? The high boiling component is salts that are formed from the quinoline, okay? And so these guys are probably going to be, upwards of about 200 degrees Celsius, this quinolinium salt. So when you form byproduct of this reaction, is you're going to keep your quinoline protonated, okay? So these salts are also going to be still in that reaction mixture. You're not doing anything to get rid of these. And these are going to be much higher boiling than what you want. Okay? And so those salts are going to cause us just a little bit of extra work. Because once you are done with your distillation, so once you get to 160, you're going to stop your distillation. Okay? Then you don't want to let everything just cool down to room temperature before you do something. You want to just cool very slightly so that you can handle things with a hot pad, okay? Then we want to get rid of that mixture into the organic waste container, okay? So we'll cool it slightly, get everything into that organic waste container. If the stir bar falls in, don't worry about it, okay? So you're going to be handling something that's hot, that, could splash a little bit on the funnel. So make sure you have your organic waste container ready to go. Dispose of it into the organic waste container. And then you're going to rinse immediately with toluene, okay? And so you want to have that toluene ready Now be careful because you're putting toluene into still relatively hot glassware, so that may splatter at you too. So be really careful doing this. We need to do it while it's hot, but you do need to be careful doing it so you don't end up splattering either the quinolinium salt mixture everywhere or even just this toluene rinse. And so you're going to rinse the whole apparatus with toluene. That goes into the organic waste, okay? And you may need to do that a couple of times, and then you'll just clean that apparatus with soap and water and acetone. So get most of what you can out of that glassware. If you get the majority of it out, then you should be able to clean things with acetone and soap and water. If there's still a little bit left, another thing that seems to work is methanol works a little bit. So you can rinse a little bit with methanol too, okay? But be really careful with this because we're doing this hot, okay? And you want to make sure, so we've emptied waste containers, so just make sure that when your waste container is still empty before you put this into the waste container too, because you don't want to get what's in the waste container to splatter back at you as well, okay? If you let it cool down completely, what it forms is this like polymer salty sludge, and you can't get it out of your apparatus. Like your apparatus won't be able to be used anymore, okay? So that's why you want to get it out while it's hot, but you can handle it, so let it cool just a little bit, get everything out of there, but again, use caution doing that, okay? And definitely, through all this, make sure you're wearing gloves, and make sure, use your hot pad handling glassware so you don't burn yourself, okay? So then, once we've got our styrene, we need to then take it on. We're going to do the step 3 reaction, okay? And so our step 3 reaction is the polymerization of the styrene. And again, we're using a radical mechanism, okay? So we've got, we would call this guy here a free radical polymerization. And for the styrene, where do you think that you're going to get that radical based on information that you have from last week? What type of radical are you going to form? Where did you form the radical last week? No one remembers. Benzylic position maybe sound familiar? So this time we're talking about styrene. So we've got a double bond that is going to be eliminated in this process, but again, we're going to form our radical in the benzylic position, okay? So in this linking of all these styrene monomers, remember that you're forming it there and not here, okay? And so we'll look at here that mechanism. It starts with using our AIBN, okay? So we talked about that a little bit last week, that it's similar to the benzoyl peroxide. Here's our source of radicals to start this chain reaction, okay? And so we take our AIBN and we're going to heat it, and we will form 2 radical species from that AIBN, okay? Then that is going to start reacting with the first styrene. So at the very end of your polystyrene, you will have a portion of an AIBN molecule at the end of each chain, all right? So you start this radical chain reaction, and then once we've got one radical formed, then it just keeps reacting with styrene and keeps forming longer and longer chains, okay? And so, again, you've got radical reacting here at the double bond, one electron this way, and then radical formed here at the benzylic position, then reacts again, and it keeps going with that reaction at that double bond, okay? Now the thing to be careful with the AIBN is you need 30 milligrams of AIBN. So in grams, how much is that? 0.030, right? So very small amount. What do you think will happen if you use too much AIBN? Go ahead. You'll get a lot of polymer, but it'll be really short polymer because it is what is starting that chain reaction. And if you get lots of chain reactions started with your styrene, you're not going to form very long polymer strands. You're going to have all short polymer strands. And so we'll talk about in a minute what that will mean as far as isolation, okay? So you want your polymer strands to be as long as possible, all right? So make sure you use only 30 milligrams of AIBN, not any more than that, so 0.03 grams. Just like the benzoyl peroxide, you do need to, it forms radicals. So it's a very reactive substance. You need to, we keep it in the freezer like the benzoyl peroxide. You've got to be careful handling it. We don't want to let it sit out. You know, once everybody's done using it, we'll put it back in the freezer. And just like with benzoyl peroxide, you don't want it on glass joints. You don't want to grind it or anything because it is really reactive. So you don't want to prompt it to react on you before you're ready, okay? But with the heat, we will get the radicals formed from the AIBN, okay? So then, once you have formed you've got your reaction from your reflux of forming the polymer, then what we need to do is have a way to isolate that polymer, okay? And so here's where the short chain and the long chain polymer comes into play, okay? As far as toluene is concerned, which is your solvent for this reaction, you're going to have your styrene and your toluene and the AIBN in this reaction. Both monomer and polymer are soluble in the toluene. What we're then going to do is cool that reaction mixture down to room temperature. You're going to get 150 milliliters of methanol stirring really well in a beaker, and you want to keep it stirring throughout the precipitate formation. And you're going to very slowly pour that toluene mixture into the methanol mixture, okay? And the reason for that, with the methanol, long chain polymer is not soluble. Short chain polymer and monomers are soluble in the methanol. So if you use too much AIBN, you're going to form all these short chain polymers which will not precipitate out with your methanol, and you're not going to really isolate a whole lot of stuff, okay? So we want to work towards long chain polymers being formed, so then this precipitation will work out that you actually get your polymer out of the mixture, okay? So with this precipitation, you are going to lose a little bit of material because you're not going to precipitate out any short chain. You're only going to get the longer chains to precipitate out. Now with that precipitation, you also want to be careful. That's why I tell you to do it slowly, because you don't want to get any globs or like kind of floating big globby masses in the methanol. What that means is things were poured in too quickly, and the toluene itself is kind of stuck on the inside of the methanol. So you get these globs of toluene and the polymer kind of stuck, and it won't really form precipitate. You'll just have the globs themselves, okay? So what you want, your polystyrene should be fairly, should be flaky, not globby. Okay, so you're going to form this white solid that when you scrape it out of your Buchner funnel is flakes, not globs. If you have a lot of globs, that's going to slow down the filtration. Also, if you have a lot of not so long chain polymer, that'll slow down the filtration when you isolate your polystyrene, okay? So you're going to isolate this by vacuum filtration. If either of those cases occur, you're going to slow down that filtration quite a bit. So you want to be really careful with the setup of the reaction and then how you go to work it up. Now another thing with this reaction is you'll want to note from last week what your bromoethyl benzene looks like before you even go into the styrene reaction, because it might have changed. It might be darker, it might appear different, okay? So you're going to get out of the reaction as much styrene as you can, and it's going to vary from person to person, but we want to make sure you have enough styrene to go on into the third reaction, okay? So you're going to get styrene from your instructor before you go on to this third reaction. We're going to help everybody out with about 1 milliliter of styrene to make sure everybody is successful in this third reaction, okay? And it also helps with the polymer formation and the solid that's formed to make it form a better solid for filtration, all right? So make sure that once you have isolated your styrene from step 2, before you go on to step 3, that you talk to your lab instructor about getting more styrene, okay? But now what you got to keep track of is how much of the styrene is yours and how much of the styrene did you get from your lab instructor. So you need to know the weight of the flask with your styrene in it, and then get more from your lab instructor, and then know the weight of the flask with both styrenes in there to be able to figure out how much you got from your lab instructor, how much that milliliter or so weighs, all right? Now with this formation, make sure you're constantly, with the polystyrene precipitation, you want constant rapid stirring too, okay? So that's usually a question is, once you start adding it, do you keep it stirring? And yes, while you're forming that precipitate, you want constant rapid stirring of that methanol, okay? All right, so then once you've got your styrene and your polystyrene, we've completed all 3 steps. We need to make sure that we characterize all of our steps as well, okay? So last week we had 2 tests. We had the density test relative to water for your final product and ethyl benzene, and you also had the silver nitrate test. So step 1, you already know what that characterization is, okay? For step 2, your characterization is going to be the boiling point range of the styrene that you collect. Okay? And that's all. We then go on and immediately use it into step 3. So that's all the characterization we have of that styrene is what boiling point range do you collect that styrene over. Step 3, we're going to use IR, and then we're also going to use GPC, okay? And I'll talk to you in a minute about what GPC means. For IR, so a couple weeks ago with experiment 6, you all collected IR spectra of your unknowns for experiment 6, and they were all liquids, okay? This time you're going to have a solid. So the only difference here is you'll collect the background the same way with the anvil up, but when you go to collect the IR spectrum of the solid, you're going to put the anvil down. You put your solid down where you put the liquid down before, put the anvil down for the collecting of the IR spectrum, okay? And that you can do, hopefully you get that done in lab, but that can also happen in open lab if it needs to, okay? And IR spectra collection is one of those things you don't have to tell a prof you're in there, okay? Just make sure when you're done, you clean it up really well. Sweep up any polystyrene solid, and then we're going to use THF instead of acetone to clean up the ATR because polystyrene is more soluble in the THF than it is in the acetone, okay? And then we're going to talk about here in a minute GPC. The one thing I want to say about that is we need your sample before lab is over this week, because we will be running those samples right away this week. So make sure before the end of lab we have your GPC sample, and I'll tell you in a minute what that means, all right? Now, couple things for yields as well, and then we'll talk about GPC itself. Okay, so we talked about this a little bit last week, step 1 and 2, yields, remember, those are going to be traditional. You'll find a theoretical yield. So you have to calculate these again. You have them in your pre-lab, but you have to calculate it back based on the actual experimental data, and then you'll figure out your percent yield after you with figuring out your limiting reagent and then theoretical yield. Step 3, you're going to have a weight percent yield, okay? So remember, you're going to take your grams of styrene and divide that, whoops, sorry, got it backwards here. Grams of polystyrene on top. Divided by your grams of styrene times 100%. That is your weight percent yield, okay? So it is not a percent yield in terms of we found a theoretical yield and then limiting reagent and so forth. This is going to be your weight percent yield, and our theoretical yield would be as much weight as you've got going in of styrene, it should come back out as polystyrene. Okay. So now, first of all, questions with any of this, and then we'll talk about the GPC. Yeah.
Do we use like the total weight of the styrene?
Mm-hmm. Yeah. So whatever. So it's your weight of styrene plus the extra that you got from your instructor is your total, the styrene mass that you want to use for this calculation. All right. So now let's look at what GPC is. So for polymers, GPC is a really common method of characterizing different polymers. What it stands for is gel permeation chromatography. Another way that this is called is size exclusion chromatography. And so the separation is based on size. And so what's going on with this type of chromatography, and we're going to talk a minute about even just in general chromatography. Usually when you're talking about chromatography, you're talking about some sort of separation technique. Okay? And we'll use quite a few different types of them this semester. With size exclusion chromatography, what you've got is this column, and it's actually a really thin column, but we've got to draw it so we can see. You've got this polymer support in this column, okay? So you kind of got these globs of polymer all in this column, and the molecules have to find their way through that column, okay? And it's kind of like, if you think of like what an English muffin looks like. So it's all those nooks and crannies, okay? So the smaller molecules or smaller polymers can sample the nooks and crannies. So they're going to travel through all of them, okay? Because they can fit in there. And when we talk about chromatography and we talk about when things come off a column or out of the chromatography, we're talking about elution, okay? And so these small molecules elute later, okay? Because they're just taking their time traveling through that column. The larger molecules don't fit in the nooks and crannies. So they elute, they come off the column faster, okay? So they're going to come off earlier. Large molecules are going to come off first, small molecules are going to come off last, okay? Because they're not going to spend much time in that column, they're just going to get through as best they can, but they're not going to travel and wind their way through all the way through that column, okay? And so, here's a little bit in your lab manual. It's kind of a schematic of what basic gel permeation chromatography instrument looks like. So we've got solvent. In this case, we're using THF. It runs through a pump. And then we've got our samples that are all going to be lined up here. The samples you prepare this week. And then we've got an injector that will inject that sample into the column. And then it'll pass through the column, and this refractive index detector will detect what comes off that column. And then we use a computer basically to put all the data together, okay? And so you'll get then a printout that'll show you your results for what happened with the GPC run there, okay? Now with chromatography, you are always talking about two things. Two things will always be involved. There is a stationary phase. Like I said, we're going to talk about quite a number of these this semester. So we'll always be looking at what is the stationary phase, what is the mobile phase. Okay? And so the stationary phase, in this case, is that polymer support, and it's a cross-linked polymer. So we talked about last week how that gives it even more rigidity in the column. So it doesn't go anywhere. It stays on that column. That's why it's the stationary phase. The mobile phase, it moves. It's the solvent that carries the sample into the column and out of the column into the detector. Okay? And so that's, in this case, that's for our experiment, we're using THF, tetrahydrofuran, as our solvent. Okay? And so when all this, the instrument itself, the computer analyzes the data as it comes out of the detector. And one thing that is run with all of the class samples is then standards that have known molecular weights of polystyrene in them. Okay? So we're going to run these standards that have a known polystyrene that is a certain molecular weight and only that molecular weight. Okay? And so when you have something in the GPC that gives a specific molecular weight and that's it, then you have a nice peak. When you have something that is a polymer or it's compound with multiple different molecular weights in it, you'll get kind of this hill or this hump there, okay? And because the polymer comes off first, you'll see a large hump there, and then if there was something in there that actually was only a specific molecular weight, it would come off as a peak, okay? But we're not going to do anything, you won't actually see the standards in the printout that you get, okay? But those standards are important because from those standards, the instrument itself sets up a calibration curve, so like you used in Gen Chem, except for its calibration curve of certain molecular weight polymer. And so then you can get the relative molecular weight to those standards and that calibration curve for your polymer, all right? And we're going to talk about here in a minute PDI, what that means. But this is more what's going to happen with a polymer. You're going to have all these different molecular weights present. And we're not doing anything in our experiment to control molecular weight. So they're going to kind of be all over the place. Probably usually in the range is 3,000 or so grams per mole up to 10,000 or so. But we don't do anything to control that. Okay, so you're going to get something that's printed out that just looks like either one hill or maybe multiple hills, but you're not going to see any nice straight peaks on there. Okay, and so we use different measurements to define polymers through the GPC. Okay, and so there's a couple things that are measured with the GPC. First of all, what's called an MN, so this is a molecular weight, and this is just a number average, and we'll go through an example here in a minute what that is, okay? Then we've got an MW that's reported, and that is basically a weighted average for the molecular weights. And so this is like, think about a mean, that's that type of calculation. The other thing that's reported is polydispersity. Okay, and what that is measuring is it takes the MW that is calculated and the MN that is calculated, and then you're going to take your MW and the MN, divide the MW by the MN, and you get this polydispersity, or we shorten it by calling it the PDI, okay? And so with this MN, what happens with that calculation is it just treats all the polymers the same. It doesn't take into account that some polymers weigh more than others. It just averages the molecular weight based on all the polymers, what's the molecular weight total, divided by the number of polymers. The weighted average puts some more emphasis on larger polymers and less emphasis on smaller molecular weight polymers. Okay? Usually your MW will be either equal to MN or greater than MN. Okay? So if you get MW and MN the same, then you have a PDI equal to 1. So if this number and this number are the same, we'll get 1, right? And that is something called monodisperse. And so that is, like I showed you with the standards, where you get just one peak. All of these standards are monodispersed. They have a PDI of 1, okay? If the PDI is greater than 1, then you're going to be polydispersed, okay? And so the polymer you make is going to be polydispersed. There's going to be a lot of different molecular weights in that polymer, right? And so now what I'm going to do is just show you an example, and this is the example from the lab manual of the difference between the calculation of MN and MW, okay? So we've got this example of different football players, okay? And so we have the number of players at a specific weight. And 1, 2, 1, 2. And then you have their weight in pounds. And so we've got 150, 180, 210, and 250, okay? So if we calculate the MN, we're just going to basically add all those numbers up and divide by the number of players. So we have 150 plus 180 plus 180 plus 210 plus 250 plus 250 divide by 6, okay? Or that's the same as saying 1/6 times 150 plus 1/6 times 180 plus 1/6 times 180 plus 1/6 times 210 plus 1/6 times 250 plus 1/6 times 250. So all of these weights are weighted the same. We're not taking into account any difference in larger numbers or smaller numbers, okay? So either way you do it, you come up with a number of 203, okay? For MW, we do take into account the greater weight of some polymers and the lesser weight of others. And so, with MW, what you do is, first of all, you find the total of those weights. So this total here was 1220. You just add up 1 150, 2 180s, 1 110, 2 250s, you come up with 1220, okay? So then with MW, what we're going to do is take 150 divided by 1220. So what portion of 1220 is the 150? And then multiply that times 150. And then we take the 180 divided by 1220 times 180 plus 180 divided by 1220, 180, plus then go on with the 210. Plus then 250 divided by 1220 times 250. So when we go through all of this math, and you see like 150 is going to have less of a weight, this number is going to be smaller times 150 than the relative 210 divided by 1220 times 210. We come up with 211 for the MW. So MW is greater than MN. So in this case, we've got a range of numbers, and hence it's a polydispersed. If it were polymers, it'd be a polydispersed sample. Okay. So you guys are probably, like I said, going to have something of a PDI. Is going to be somewhere in the neighborhood of 2 to 30. Okay. What you want to get from your GPC data is you're going to want to find MW. That should be calculated for you. You want to find MN, and sometimes it's printed out PDI, but sometimes you just have to calculate it, which I told you how to do that. MW divided by MN, you'll get your PDI. So these are the three numbers. You're going to get this whole sheet of paper with information all over it. These are the three things that you want to take out of that. Okay. Now for those samples, follow the instructions in the lab manual for prepping them. You want to make sure you use the THF that's labeled for making GPC samples, and all the materials you need for prepping are in the reagent kit, okay? You need instructor or TA to help you filter. We have to filter these samples so no little particles go through the column because it clogged the column. So have your instructor or TA help you prepare the sample. And then on the side of the sample, you want to put your initials and notebook page in Sharpie. Okay, so like TLS 52, okay, in Sharpie. Then you also want to fill out, there's a sample sign-in sheet, okay? Fill that out. So you want to make sure, give your name, give your sample ID, and then put your sample, you're filling this out where in correspondence to your drawer number. So your sample goes in this folder next to your drawer number. You're filling out the sample sheet next to your drawer number, okay? Make sure that this is really, both of these you want to make sure you can read, especially this guy, because this is what's going to go into the computer, and then this is what you're going to use to figure out which GPC data is yours, okay? So make sure this is really legible, okay? And then like I said, if you need to collect IR spectra, that can do out of lab. One more thing, for the IR, I don't want you guys to all print out, you're gonna need a literature IR spectrum, okay? So you don't need to all print out a polystyrene spectrum. I will post a spectrum on Moodle, and you will use that to compare for your literature spectrum, but again, don't everybody print it out of Moodle, just use it on Moodle to compare to your data, okay? All right.